Bahareh, Parnia, and Amin developed a computer vision approach for detecting asteroids and comets in space satellite images. Generally, when we are talking about space objects, the first thing that comes to our mind is their probable dangers to our lives. That makes sense since we've had several crashes of comets and asteroids in the history of the Earth. Let's just remember one of the stories behind the extinction of dinosaurs, which were once living on the Earth. However, besides that, there are a lot of interesting and most possibly unknown stories inside these objects related to the formation of the solar system. Not only that, interstellar objects, if detected by scientists, are expected to open a new door to the somehow unknown world around us. And it is not something unexpected. These two interstellar objects were detected by humans, which were our guests in the solar system. The comet Borisov, that was passing the solar system for a short time till some months ago, surprised scientists as they found that there exists water even beyond the solar system. There are three main approaches to detect asteroids and comets. In basic techniques, two images taken from one location in two different times are subtracted. So they expect the remaining peaks to be the moving objects. However, due to the large amount of noises in the space images, recognizing moving targets becomes impossible in cases that the asteroids or comets in the images are not large or bright enough to be recognized from noises. The shift and add method shifts the temporary images taken from one location in the sky relative to each other successively and add the shifted images together. If the shifting direction is consistent with the object's movement, the final image will show a brighter spot. But to check all possible movement directions of the moving object, the shifting and adding process must be done in all directions, which is a time-consuming and a computationally intensive process. The strict detection method adds all temporary images taken from one location in the sky. This way, a streak, which is the pattern formed by the moving object, is generated. The most common difficulty with this method is that it is generally restricted to linear or mildly curved movement of the target object across the field of view. Besides, for large objects, it is possible that the object is not detected automatically. Our approach is a strict detection method, and our goal was to decrease the dependencies of this technique to the size of the object and shape of the path of the moving object. Let's take a look at the overall process of our algorithm. We use NeoSat images. NeoSat is a Canadian satellite which takes images from the space around the Earth. We downloaded the images from the Canadian Space Agency portal. Then we detected all tracklets in the dataset. Tracklets are sets of images taken during some time from a fixed location in the sky. After choosing a tracklet, we cleaned images in two steps. First, we eliminated the systematic errors, and then we removed some noises from the images. Then we merged all the images that were existed in one tracklet. As you can see around the middle of the image, the asteroid path is visible in the resulting merged image. A line segment detection method named LSD is applied on the merged image. As you can see in the mask, which has resulted, the three types of lines remained. The object path, the noises in single images, and the borders of large stars. In order to remove extra lines, we applied LSD on single images. Then we merged all masks of single images altogether. Then we subtracted the dilated version of this mask from the mask provided from applying the LSD on the merged image. The result shows that, as we expected, all the extra lines, that is the line noises in single images, and the border lines of the larger stars are removed, and we have the path of the moving asteroid. Our algorithm shows no dependency to the trajectory shape of the moving object. While the path of this asteroid is not a linear streak, our algorithm is able to detect its path by creating and connecting sequential line segments. The proposed technique is robust in cases of having fuzzy moving targets. These fuzzy targets are generally generated by comets in space images and are challenging to be distinguished from noises. These two images are results of the recently discovered interstellar comet Borisov. Our algorithm is also tested on the recently discovered comet Neowise. Neowise has a near parabolic orbit and is discovered in March 27. Detecting this comet shows that our algorithm can also detect large targets in space images. In this table, some statistics of 3 datasets are given. These values are extracted from UN16 FITS images after they are cleaned. The proposed solution is able to detect dim moving objects. The table shows how the mean intensity of the trajectories are close to the mean intensity of their backgrounds. For example, the result for the day 292nd of 2019 shows that the object path can even be detected in cases that the mean intensity of the path has a difference of just 2% with the mean intensity of the merged image. Furthermore, the proposed software is able to find the moving object path in an image with a high level of background noise. The result of day 128 of 2019 shows that while the mean intensity of the merged image is 7% more than the mean intensity of the moving object path, the object path is detected. The proposed algorithm is capable of detecting relatively slow-moving targets, which are making short lines in a track of data, like lines with the length of 19 and 26 pixels. This approach has a low probable number of false positives, which is a big step toward detecting moving objects automatically. Besides that, we expect that this algorithm is capable of detecting various moving objects in space images rather than just asteroids and comets. This solution won the grand prize of the Canadian Space Agency Space Apps Challenge in 2019. There is also an open source user interface which is available in our GitHub link provided here. Thank you.